Today we're going to be looking at what we call the alternating series remainder. Now remember, what a remainder really finds for us is an error. How accurate are we in our estimation of a sum? Now, it's telling us that suppose that a series is alternating, decreasing in magnitude, and has a limit of 0. Now, all of this should sound familiar to us from yesterday, the day before. This is the alternating series test, and we said the test says if it's alternating, decreasing in magnitude, and we have a limit equals 0, then we're saying that the series converges by the alternating series test. So we're basically looking at a convergent series right here. And it says that if this series converges, then we can estimate the error. We can get the error, R sub n is the error of the nth term of our sequence, of our series, by looking at the next term. And it says that the error has to be less than the next term. Now, this should be almost kind of like common sense. So let's say we take a look, for an example. Let's say we have a series, looks like this: 1 minus 1/2 plus 1/3 minus 1/4 plus dot dot dot. And let's go one out one more, plus 1/5. Let's go out one more, minus 1/6. There we go. Now, this series right here, it is alternating, it is decreasing in value, and the limit as we go out to infinity will approach 0. So what we're saying here is, let's say we want to estimate what the value of this series is as we go on forever. But let's say we only want to use the first 5 terms as sub 5. Well, what the alternating series remainder is telling us is that our biggest error will be, or the most that we can be off, is the next term. In other words, the biggest the error can be, the remainder of 5 is going to be the next term. It's going to be less than the next term. And that kind of makes sense, because if this is indeed a decreasing series, well, my next term is what I'm going to be adding to this. So I can't be more than 1/6 off of the actual value of our series. We'll come back to this in just a moment, too. We can use this to answer quite a few questions. Okay, so let's say we have the series. Now, this is an alternating series, and they're asking us to find the sum of the first 4 terms. This is actually a 3-part question right here. I want to find the sum of the first 4 terms. So for the first part, I just want to find S sub 4. And I'm going to use my ever trusty handy dandy calculator. And we're just going to type this in. Let me get rid of that. We want to find the sum of a sequence, SEQ. Now, you guys know the calculator better than me. You probably at this faster. And I'm just going to type in what that sequence is, including the negative part. They're alternating. Control. I'm going to go. That's the control divide, gives you the fraction there. I'm going to go -1 to the n minus 1, or x minus 1. You can use n in this case, over n factorial x. Now, to get the factorial key, down here by the G there's a question mark. Just type that, and it's the second one over factorial. Now, type in the comma x, comma 1. I want the first 4 terms, and I just press enter, and I get 5/8 right here. So the sum of my first 4 terms is 5 over 8, which is 0.625. I'm going to write that as a decimal for what we're going to use with it later on. Now, the next question, the next part says and explain why our estimate differs by less than 1 over 100. This is part 2. Now, what part 2 is asking me to find is my error. It says find the actual error. In other words, what is the most we can be off by? So to find my error, I have my formula here. Now, I want to show that my error is less than 1 over 100. So I take a look. My rule, R sub n, which is equal to, now remember this S minus S sub n, we talked about this before in the integral error. This is my actual value minus my first 4 terms, my partial sum. This is going to be less than the next term. So if I want to find the error of the first 4 terms, remember, I'm approximating my sum of this infinite series to be 0.625. I just want to find out, well, what's the most I can be off? Well, the rule says for alternating series is the most we're going to be off is by the next term, or a sub 5. Well, how do I get the 5th term? Well, my 5th term, I just plug it in here. What's 5 minus 1? 4. So I get 1 over, and this becomes 5 factorial. So therefore, my error is going to be less than 1 over 120. In other words, the most I can add to my next term is 120, 1 over 120. So take a look here. Is 1 over 120 less than 1 over 100? Of course it is. So therefore, we can say by the alternating series remainder, and that 1 over 100 is less than that 1 over 120, our remainder, our error of the first 4 terms is also going to be less than 1 over 100. It's kind of lengthy the way to write it, but that's what we do. By the alternating series remainder and the fact that 1 over 100 is less than 1 over 20, our error is also going to be less than 1 over 100. Very easy to do these. So now we actually have one more part here. Now the next part says, well, let's use our results to find the interval in which the actual value must lie. This is part 3. Now for part 3, it says I want to find the interval of the actual sum. And again, I can use my rule up here. It says that the difference between my actual value and the first 4 terms of my sequence has to be less than my next term. Well, I know S sub 4s. I found that right here. So this is just S minus 0.625. We know that it has to be less than my next term, A sub 5, which we already have here, which we know is 1 over 120. And I just solved this. My actual sum minus the 0.625, my approximate value of the first 4 terms, is less than 1 over 120, but can be greater than negative 1 over 120. And I just solved this. Okay? Using my ever trusty calculator, because my arithmetic is terrible. If I take 1 over 120, 1 divided by 1 divided by 120 plus 0.625, I get 0.633 repeating. And if I take this negative 1 over 120 and I add 0.625, we get 0.616 repeating. So we're saying that the actual sum has to be between 0.616 and 0.633. So it's pretty accurate. We only have 4 terms, but look how close we are to the actual answer. About less than 2 hundredths of a decimal off. Very easy to do. Alright. Now, the next part says, okay, well, what happens if we know what we want our error to be, we just don't know how many terms we have to go out? And that's what this second part says. The second question, it says, how many terms are needed if I want to make this series, if I want to find the sum of this series, so that the estimate, or S sub n, differs from the actual sum S by less than 1 over 1,000. Well, that's just my rule. Remember, R sub n, which is the difference between S and S sub n, which has to be less than our next term. So I have to find out, what I need to find out here is how many terms are needed. So there's a couple ways I can do this, okay? I don't know what n is. We're trying to find n. That's what we're looking for here. Well, my next term I know has to be less than 1 over 1,000. So I can kind of set that up here. R sub n has to be less than 1 over 1,000. So what I'm going to do is I'm just going to list out my terms. There's actually two methods I can do for this one. Method 1, I can just list out the number of terms, list out all my terms. N equals 1 to infinity, negative 1, n plus 1, over n factorial, n to the fourth, sorry. If I just list them out, plug in 1 here, we can get 1 over 1 to the fourth. It's alternating, so it's going to be minus 1 over 2 to the fourth, plus 1 over 3 to the fourth, minus 1 over 4 to the fourth, plus 1 over 5 to the fourth, minus 1 over 6 to the fourth, plus 1 over 7 to the fourth, and you can kind of see it goes on forever and ever and ever. I can find their values. This is just 1 minus 1/16 plus 1 over 81 minus 4 to the fourth, 1 over 256, plus this is 1 over 625, and 1 over, I think that's 1296. Now, notice it does go on, but I can stop here, because this is my a to the nth plus 1 term, because this is already bigger, or smaller, excuse me, than what I was looking for. So this is smaller than what I was looking for here. So I'm just going to back it up 1 here. That's my a sub n. That's my nth term. So therefore, if I count there, what's n going to equal? 1, 2, 3, 4, 5. I get n equals 5. And there's our answer right there. Now, there's another method we can do for this one, and it's a little bit easier to do. I just want my remainder here to be greater than or equal to 1,000. So I just need to find out, well, what value of n is going to have that happen for me. Remember, so what I'm going to do, I'm trying to find n, right? So I can just do this, 1 over n to the fourth less than 1 over 1,000. And if I solve this, I get n to the fourth is greater than 1,000. And I'm going to use my calculator here. I don't know what the fourth root of that is. N is greater than, I take the fourth root of 1,000 to the 0.25, I get 5.62. Now, be very careful. I want it to not be I don't want to go that high. I don't want to go any bigger, so what I'm going to do is n is greater than or equal to 5.62. Well, I only have to really go out 5 terms, otherwise I'm bigger than what I need. So, therefore, again, n is 5. All right. Hope you guys had fun with this. It's pretty easy to do, and we'll see you later. Thank you. Bye-bye.